Hey guys, and welcome to the last part of the easy challenge. This is going to be the last set of problems we're going to be doing for this challenge. I might be doing more in the future, but for now, for the next coming weeks, I'm not going to be doing any more easy problems most likely, unless maybe there's a problem of the day or something. So I'm going to try to think of some other stuff to do. And if you do have suggestions on that, feel free to write them in the comments or whatever. So let's get started. Given two binary strings, A and B, return their sum as a binary string. Okay, so let's just do, I think we want to reverse them. Yeah, it'd be easier to reverse them. I think this works in Python. Let me just double check. I should turn this for now. Ooh. Oh, okay. I guess I can't answer, that's fine. Okay, so now what I need to be doing is I need to be going through every single letter, so we need to have a res. This. And then we also need to see, yeah, okay, so let's just index. And we'll just do a while true type of thing. So if index is less than length A and index B, we have a number for both. So how would we want to do this? I think we'd want to just add them. So temp equals, yeah. And then we'd also probably want to have a cin, right? Yeah. Okay, so let's just do that. I think. Yeah, so temp equals A index plus B index. Yeah. And we also need to do, and we need to make them integers. This definitely is not super easy of a problem, to be honest. Just hopefully the next one's gets easier. I mean, there might be a cleaner solution here for sure though as well. So plus cin. Okay, now we have some output. So res. Yeah. Append. So we're going to need to have this be a string. And then it's going to be temp mod 2, I believe. Right, so it's 1 on 1. Yeah. Okay. And then C out is going to be temp divided by 2, I believe. What the heck? Okay. Okay, I believe that's right. Yeah. Then we just do, and then x plus plus. Elif index is only less than length A. That means we just do we only take the A value, so let's do something like this. So this is index A. Okay. Then res.append. Yeah, so that part should be right. That code. So it's definitely repeated code, but it's okay. Else elif index is less than length B. We do all this crap for B. So B index. Okay, that's fine. I don't think I repeated code, but whatever. Definitely can optimize. Else we break, and then we also have to have if we have a cin, right? Yeah, cin res.append 1. Okay. So now we have that. And then in which way would that look like, right? So we would be adding backwards. So I think we need to flip the res. Yeah, so res equals res this. And we need to return a join of the res. Okay. Let's see here. What is not? Oh, append? No. Okay. Alright. I mean, if that's alright, that's pretty sick to be honest. With no errors. Okay. Given an array nums, return instinct numbers. Return the only number that's missing. Okay, that's pretty straightforward. I think we've had a lot of these problems. So we want to append another index. Let's just append 1 here. Then 4. Do we even need to do? Sure, let's just do it this way just in case we need it. Length nums -1. We don't want to go to the last value. Then we want to say nums. Yeah, I don't think we even needed to do for I in range, but whatever. And this is abs. Actually, this is nums abs I. So this is if nums abs I is greater than 0. We just make it negative, so we can copy all this shit again. Nums abs I times equals -1. Okay, I think that should work. Let's just print it real quick. Actually, let's just try to return and see what happens, right? So we'd want to loop through this again. Yeah. Now, okay, now we need to loop through the whole thing. Yeah. If nums I. Oh right. Oh, so okay. So the problem is this. So we actually need to change a little bit. We can't make them negative because you can't have a 0 value. So let's do that. So if nums, and let's just have some big int, right? So big int, big num or something equals 10 to the 6, let's say. Okay. There we go. Now let's change this code. Actually, we need to change it. So if, and let's just say temp again. Once again, we can definitely clean this up, but it's okay. Nums I. If temp is greater than 10 to the 4th, temp minus equals 10 to the 6th. So that'll give you our value. Okay, now we say if nums temp is less than 10 to the 6th, nums temp, let's just say 10 to the 4th actually, or 10 to the 5th, whatever. Actually, let's just use 6 here. Let's make this other number like this. Okay, so temp minus equals 10 to the 8th, or this is actually, it should just be big num. Okay, if temp num is less than 10 to the 6th, then 10 num plus equals big num. Okay, I think that's all for that. Then we need to loop through it again. If nums, except this needs to go here, nums I is greater than, or less than, sorry, 10 to the 6th. Okay. Return I, because that would be your value. So it's definitely not the cleanest code, but it works. Okay, and I'll go over it. Alright, reverse bits, K2's complement. Okay, so how do we do reverse bits? Okay, so I think what we need to do is we need to, so this could be a 32, so we have to do this operation twice. So we can have like res equals 0. We can't have while n, I don't think. Yeah, we can't have while n is greater than 0, so we have to actually have a counter. So for I in range, and then I think we have to do that 32 times, I believe. So this is just 32. Yeah. Okay, so res equals res this, then res plus, let me think. What do we need to add? Yeah, so we need to plus equal the number n and 1. That would give us, if it has a 1, we'd need to put it in the res. I think this is right. Then we need to shift the nums the other way, hopefully. Okay, hopefully it's right. We might be like an off by 1 error. Oh my god, that would be insane. Okay, nice. Given an integer and return array of, okay. Number of ones in the binary representation, n2 output. Okay. Okay. So let's think about this. Given an integer n, return an answer of length n equals 1. That this is the number of ones in the representation. So what would 2 look like? So 2 would be like this. Right? So why are there 3 ones? 0, 0, 1, 1, 2. Okay, let me reread this one more time. Given an integer array n, return array ands of length such that for each number of ones in the okay, so it's every single one. Okay. And this is the number of ones? How is this an easy problem? Or how is this how is this an easy problem? Am I missing something? 0, 0, 1, 1, 2. I think am I getting it? Not really. Huh. I mean, let's take a look at this 5. So 0, 1, 1, 0, 1, 1. It's like we're doing a binary add, which is not that easy. I mean, I guess since it's an easy problem, O of n, can you do it without any built-in things? So there's definitely a tricky solution, but I think for now maybe we just code up the easy solution. Do we want to do that? Yeah, let's just do that, right? So let's just do that. And then we'll think about the more difficult solution in the future once we come back. Okay, so let's just say res equals this for I in range. So we're doing 0 to n. Yeah. Okay, so n plus 1. So then we have to do this count number of ones thing. So that's pretty straightforward, I think. Temp equals n. And then we have to have ones equals 0, let's say. And then we just do while temp. Sorry, this is I. While temp is greater than 0. If they're actually ones plus equals temp and 1, which would give us the last value, and then we just do this, right? And then we just append ones to return that. Okay, so that would be the n log n solution, but we'll definitely come back and figure out the other one. Number of 1 bits. Okay, so this is just really straight. This is the easy one. So this is the same code. Pretty much we're just going to change it around a little bit. So except, actually, sorry. So we need just this code. So let's get rid of that. We don't even need these temp. Yeah, so we don't need this res. We don't need this. While n is greater than 0. N is 1. So this is the easy problem. Yeah, I don't know how the other one is. Okay. Return. And then this should actually be like this, right? Hopefully we don't have any tabbing. Okay. Okay, given an array, every element appears twice, except for the first one. So I think I've seen this problem already, but I mean the trick to this is really straightforward. So for nums, we need a res res XOR equals num, return res So when you have duplicate numbers and you just XOR the whole array, you should be able to get the output. It's very straightforward, but we'll talk about it for sure. Roman integer is just represented by whatever. Okay. Okay, so we have all these cases. I think this is just literally a bunch of if-elses. Yeah. I mean, there's definitely a cleaner way to do it, right? So the cleaner way to do it would be yeah, so the cleaner way to do it would be whatever, but we're just going to do the brute force and then I'll talk about the cleaner way, kind of. And um, I think time-wise it shouldn't matter. So let's just alright. So let's just do all of these. So if si equals this one, we need to check if I is less than length s and psi plus 1. Actually, we could do this. So this should be clean. Actually, no, that would not be clean. Yeah? Would it be cleaner? Yeah, I think this should work. Okay, and then this is going to be s plus 2. Yeah, I think that should actually work to get 2, and then even if we're out of bounds, we're fine. Yeah, okay. So if this equals, yeah, so what are the things? So this is one of them, res plus equals. Oh, we don't want to do this for I in range, actually. We want to have an index, so because we're going to have to go forward sometimes. So while index is less than s. Okay, and we can just make this I, actually. Okay, there we go. So 5 plus 2, res plus equals 4, elif. So the other case, it's this, and then index we'd have to increment it here. We'll increment it by 1, and then we'll increment it. Okay. Now this is I. So the other case is this, which is res plus equals 9, I plus equals 1 again, else res plus equals 1. Okay, elif. So what are the other cases? So we can have a v, and v can't be placed before anything, right? Yeah, so if it's v, so let's do v, then we just do res plus equals 5. Yeah. Okay. elif si. What's the next one? X. So this does have multiple cases. So let's actually copy this code here, because this is going to be pretty much the same thing. Okay, so X, and then what are the things it can be? XL, then XC. Okay, so XL is what? 50? Or sorry, 40, 90. Okay, else, and X itself is 10. Okay, and let's just be an elif here. Okay, next. Yeah, so a cleaner way would be to put this in a dictionary, like all these, and then you can just do a constant lookup instead of doing this huge else if thing, but whatever. Si equals L. So what can L be? No. So that's pretty straightforward. Res plus equals 50. Okay, elif si. What's next? C. Okay. Okay, can see. Yeah, so we need this if else thingy. So it's CD or CM. Okay, so if CD is 400, 900, and C is 100, elif si. I mean, this is definitely not clean at all, but you know, it's okay. D. Okay, then we have res plus equals 500. And then the last case, let's just have elif, but this should only be, this should have to be this, the last case. So m res plus equals 1,000. Okay, so those are all the things it can be. Now we just do index plus equals 1, turn res. Okay. Line 5. Probably had some syntax there somewhere, but let's see. Okay, so oh yeah, this s plus 2, this should be I. Just copy that to the other stuff. Okay. Definitely not the cleanest code, I'll say that much. That's okay. I'll talk about how we could optimize it once we go over. I. Okay. Alright. Shift 2D grid K. So I think this is straightforward. So we're shifting a grid K spaces. So we need a linear grid. I think this needs to be the size. So we'll just make these zeros. Yes. So let's just make these zeros, and then it's going to be the size of, let's make rows and columns as well here. So, okay. Rows, columns. Yeah, these are definitely not as easy as the other easy questions, but that's okay. This is the last easy. So, this would actually be completely wrong. Again, my brain is frying. So length grid. Okay, length grid 0 times rows, and this should be rows times columns. Okay. Now we need to do K. So K equals K modded by rows times columns. Right? Yes. Yeah, because if this is 9 and we're shifting like 18 times or whatever, it's going to be, yeah. Okay, so now we're getting somewhere. So now we are definitely getting somewhere. So let's just say, how do we want to do this? Okay, so we want to start by putting things into K. Yeah, okay, so let's just loop through this for row. And let's actually have another value for temp, just because I think we're going to need to use it, so that's fine. So for row in range rows, we need to loop through this thing for column range columns. And then I think that, where does the first element go? So we need to shift 3 times, let's say, then the first element which would go into K, right? Yes. And then the second element should go into K plus 1. Yeah. Okay, that seems right to me. Okay, so linear grid K, let's just do these as temp, equals grid row column, and then temp equals temp plus 1, but then we need to mod it by this thing again, because, yeah. Okay, that should be good. Let's just print this out just to see here so we don't make too many mistakes. So let's take a look. So this 3, yeah, so this is the right order. Perfect. Okay, so now, pretty straightforward. We're going to have some kind of variable again. Let's just use this temp. Why not? Okay, and then same loop. Now we just, pretty straightforward. So this is grid row column equals, then we insert from the linear grid temp. Okay. What? Actually, list object is not callable. No. My brain is definitely fried. Okay. Alright. Did it work? That's ugly number, ugly numbers. Okay, this one's really easy, I think. So if, okay, while, let's see here, One has no prime factors. Okay, can it be 0? It can be negative, okay. I think 0 would not be an ugly number. Okay, so let's just say, what do we want to do? I think what we want to do is we want to do absolute value because I think that doesn't really matter. So that solves that. Now while n is greater than 1, I think is what we want to do here. Yeah, so, and then we would just want to do, okay, here we go. So if n mod 2 equals 0, then do that, right? So n equals n, or we can just do n divide equals by 2, I believe. Elif, oh, what is going on? N mod 3, so 235, yeah, so n mod 3, okay, elif n mod 5. We actually don't even need to elif because it's okay to do all of these. So, okay. Actually, no, we do need an elif. We do need an elif because we need to make sure that one of these works. So else, here's where we need to return false. And then here, we just do return, and then this should be 1. Okay. Yep. What? Oh, I see. So this actually got changed to a I think when I made this absolute value, it actually changed the value. Okay, fine. So, whatever. So while n is greater than n, or n is less than -1, or n equals -1, or we can just do n doesn't equal 0, right? So anything other than 0 is fine. Okay, I think that should be good. What? Output true, expected false. How? Okay, I guess let's just print this. So let's use this test case, and let's print n. Let's see what we get. Okay, we get -1. Oh, I think it's because maybe it's too big. Is that it? Like there's some overflow thing? I don't understand. Like what is this number so special? Like we do get -1. Or can we not have negatives do they want if n is less than 0 it doesn't work? Is that what they want? That's the only thing I could think of. So, is that what they want? Which, okay, there we go. So, okay, interesting. So they just didn't want negative numbers. Weird. Okay, pounder number, return x. Okay. Okay, so for one thing, we know that if x is less than 0, return false. So I think all we have to do is just turn it into a string, right? So x equals str x. Now we just do return. So we could do the left and right pointer, or we could just do this. Technically, I mean, do we want to do the left and right pointer? Nah, I think we'll just save some time. We've had enough of that. Equals x. Should work. Nice. Yeah, okay. So let's go back and go over these. Okay, so for the first problem, what do we have? So we have given binary strings, return their sum. Okay, so it's pretty straightforward. So you flip the strings because you're going to be adding backwards, right? Like let's say you had some numbers in normal math. Let's say you had numbers like this. Yeah. You're going to want to add backwards because, do you want to add backwards? I think so, right? Maybe you actually don't. Yeah, maybe you actually don't need to. Maybe I was wrong about that. Let me think. Yeah, I think I see. So the reason, so you actually don't, but the reason I flipped them was just to make it easier on myself, because if we add from the end, then we don't know what index we're at, where if we flip them, right? So if we add like this, now this is index 0. So that's why I flipped them. Because we can just add from index 0 instead of from some end index that we don't really know where to add from. So I think that's why I did it, which, you know, either one's fine, so you don't have to flip them. But pretty much all you do is, like, let's say you have something like this, and you're adding these numbers. All you're doing is you just convert these numbers to integers, and then you have a cin, and then you have a cout, right? So your cin starts off as 0, but then when you add these two, you get 2. And so the way to figure out what number to put in is we mod whatever number we get here by 2. And if it's a 1, then this would be a 1, right? Because when you add binary digits, so this is going to give you a 0. So the only way to get a 1 would either be you have a 1 and a 1 with a cin of 1. That would be 3, which would give you a 1, which is what you want, right? Or something like this. So either one of those would give you a 1. Otherwise, it's a 0. And then for your cin, it's like your carry. So when you add two things, in order to figure out if you have a carry, your sum has to be 2 or more. Because if your sum is 2 or more in binary, you carry over, right? Like if you add something like this, let's say, you add these two numbers in binary. So there would be no carry to begin with. So this would be 0. Now there would be a carry. So you'd have a carry here. Now this would be a 0, but we had a carry. So we put in a 1. And then we have a carry left over, so we have a 1. And that's why we had this cin at the end, because we might have a carry at the end. So all we're doing is we just have a result list, and we're just adding bit by bit, like a normal addition. You know, if you want to figure this out, like just think about how you would do a normal addition of some numbers, right? Like something like this, how you would do it. You would add them together, and then you would have a carry bit, right? Because like if this 3 was a 7, then you'd need to carry the 1, and so on. And the carry bit starts out at 0, but then at the very end you also, like in this case, let's say this is 0. Now you're actually done with these lists, but you still have a carry in bit, so you need to add a 1 at the end here. So it's pretty straightforward, just addition. If you need practice with that, then feel free. So the way to tell, this is also pretty, I mean, these are definitely tougher than the easies that were like in the first easy. So this is pretty straightforward. So you're saying we have numbers 0 to n. So if you think about what indices do we have here? So here we actually have indices 0 to n minus 1. So like 0, 1, 2, right? So if you have this, 3, 0, 1. This would be index 0, 1, 2, and we actually want another index. So what I did is I just put in another number that I'm never going to use, so let's just put in a 1 here. Then you iterate through this list, and you go to, if these numbers do exist, you go to that index. So like let's say here, we would go to index 3, and then we would just add some huge number to this number. So let's just make this, let's say, we don't want to make it infinity because we want to still be able to get this index if we need to. But let's just say this is like 1,000,000 or whatever, right? So this is a million, then we go here, then we make this, you know, 1,000,003. But we can't always go back, right? Because if this was a 1, it would be 1,000,001. So we can just say if the number is really big, just subtract a million to get the original number. And so we can actually show you what this looks like here. So if we print nums. So you're just going to every index and you're adding a big number so you can see what this looks like. And whatever index you didn't add a big number to is the index that is missing. And this would be index 2. I think we actually had a couple problems pretty much like this one. So reverse bits, I was actually amazed that I did this right away. But let's say we have just some number like this or something, right? For one thing, we can't just say until the number is 0. We can take the bit because the problem with that is the reverse of this would actually be this. But the number would be 0 right after we get rid of these bits. So if you just say so we're doing this and so first of all, let's just show you how to get the last bit really fast. So if you have a number like this, to get the last bit of a number, you just AND that number with 1. So if you AND this number with 1, you get the last bit. Now we have some res. So what we do is we AND the number, then we store that in res if it is a 1, and then we shift the res this way and we shift this way. So by the end, this 1 that's over here will be all the way to the left in the res. So you're moving one way and you're moving the other way, and you're just adding whatever digit is here to here, and then you're moving them over. So like you would have the 1, then you would move it the res, and you'd have a 1. Now this would move, so this would come off. Now we'd get another 1, so we'd put a 1 here. Then we'd move it again. So now we check this digit, and then we put it here. Check this digit, put it here, and so on. And then we just have a, you know, there's 32 bits in a number, so we just have 4i and 32. And then you see we're shifting the number to the left, and we're shifting the rest to the right. It's very easy to have a off by 1 mistake or something, so that's why I was kind of surprised I got this right away. But yeah, and this counting bits is pretty much the same as this reverse bits. Like reverse bits is counting bits with some more steps. And the way to count bits. So by the way, so there is a better way to do this problem, I think. So let's just think about it really fast. How we would do this in a cleaner way. Maybe instead of doing that here, because this video is getting kind of long, maybe I'll do another problem on this counting bits exactly, and to show how to do the optimal solution, because that's going to be more of a medium or hard, so I don't want to do that right now because this video is actually getting kind of long. But the simple count bits that you would be expected to do for an easy problem is you just simply have some number, right? And you just keep ANDing it with 1, and then you have some res that says how many times do you get a 1, and then you keep shifting it over here until it's 0. Okay. Yeah, and if you want to, I mean, people are pretty rusty with their bit manipulation, so these are definitely, if you make sure, if you want to learn bit manipulation, if you want to save it for interviews altogether, that's probably fine. You don't really get tested too much. But if you do want to learn it, these problems are good to do the easy stuff, because the later problems will have some like bit masks and things, and if you're not comfortable with just simple bit shifting, then you're going to have some trouble. Okay. Yeah, so this counting bits is literally we loop through every single number, 0, 1, 2, whatever, and we just do that. And then this number of 1 bits is pretty much the same thing, except now you only have one number. We don't even loop through anything, so it's the same thing. Single number. Okay, so the trick, I think I may have gotten over this before, but if you have some numbers, and you have, I think this is common enough, where every number appears multiple times, and they have to appear, it depends how many times. So if you have a number appear twice or 4 times or so on, if you XOR every single number, all the duplicates will cancel out, and you'll get your final answer. So let's actually try that real quick just for these couple examples to show you. So 2 is going to be 1, 0. And so our res is going to start with 0, right? So it's going to be, it's going to start with 0. So XOR, so it's going to be like this. So when we XOR 0, 0 and 1, 0, XOR means we have a 1 or a 0, right? So 0, 0 with whatever is going to give you whatever it was. So this is 1, 0. Now we XOR, so we have this 1, 0, now we're over here. We XOR this 1, 0 with this 1, 0. A number XORed with itself is 0, because you're going to have the same digits, and XOR means one or the other, right? Okay, so a number with XORed is 0, and then we XOR with a 1, and we get 1. So because a number XORed with itself, the order doesn't really matter. Like we can have this, it'll still work. You can try it out. So that's just a shortcut. The other way to do it would be probably have like a set. Yeah, you can have a set of all the numbers, and then or I'm sorry, not a set. It would be like a hash map of counts of every number, and then you just look which one has a count of 1. That would be pretty straightforward. But this XOR is kind of clean and kind of cool. So okay, so this I kind of definitely did a brute force. What we could do instead is we can have a hash map of all these values. So we can have a hash map of like I, V, and so on. So that's how we would take care of that. We would get 1, right? So what we can do is like we get one character at a time. We say like, oh, we got an I. Okay, cool. Now we know it's a 1. But the other thing we need to do is for this I, X, and C, we also need to look at the 2-letter combination, right? So if we got an I, we can say, okay, let's take the symbol after it, and let's see if that appears in our hash map. So when we get like IV, we can also store these in our hash map. So we can store IV in our hash map. We can store IX in our hash map, XL, XC, CD, and CM. And then actually what we can even do that's cleaner is we can try to see is there a 2-letter segment available where we're at, and if a 2-letter segment is in our hash map, take that first. So just gives us priority. So like let's say we have a string like stuff. Let's say, obviously these aren't Roman numerals, but we're at this index. We can just say, is there a 2-letter segment? Yes. Okay, is that 2-letter segment in our hash map? If it is, get the value, right? If it is, get the value, and then just move on. And then if it isn't, then get the 1-letter segment and get the value. So that would be the cleaner solution, is just store all the 1 letters and all the 2 letters in the hash map and just look in the hash map instead of having these 50,000 if else's. Okay. Shift grid, pretty straightforward. So what you can do here, 4, 5, 6. So first of all, for this k shift value, like you need to shift the grid k times. Once you shift it more than the entire grid of values, we're just going to be at the same spot, right? So let's say we shift 9 times. Well, 1, 2, 3, 4, 5, 6, 7, 8, and we're back to where we were. So that's why I have this k equals k mod rows and columns, because we're back to where we were otherwise. So all I'm doing is I initialize an array that's as long as this whole grid. It's just a one-dimensional array, so this will be 9 elements. And then if you think about it, so if you're trying to shift something, let's say 3 times, right? So for k equals 3, well, where would that go in our array? Like, so we want our resulting array to be the numbers in the exact order. So this resulting array, if you look at over here, should be like 9, 1, 2, 3, and so on. We want the numbers that we're going to actually be spitting out. And so you could see that the 1 gets shifted, the 1 gets shifted here 1 time, but in my case, it gets shifted 3 times. And so if I want to shift the 1 3 times, then this would have to go to index 3, right? So, or sorry, so this would be 1, this would be index 3 to 1, 0. So that's what I would do. I would put the 1 in index 3, and then I'm just traversing down this nested for loop. And then I keep incrementing k by 1, right? So then k will be 4, 5, and so on. And then the only thing I need to do is I need to, when I do increment the k, I need to mod it by rows and columns because I don't want it to go out of bounds, right? So if this k has a length of, let's say the max index is 8, when I'm at 8, and I would be at 8, like somewhere around here, I don't want to go to 9 and so on, right? So I just mod the k by the length of this array to make sure that once I'm out of bounds, I go to 0, because I didn't start at the original index, so I will be out of bounds. So then when I do have this array of elements, let's say I have whatever elements, right, 2, 3, 1, whatever, then I simply loop through this grid again, and I start at the first value, and then I just write from the first value to the first index, and then I move the index 1 and so on. So I write all these values into a one-dimensional array, and then I write them back. So that's pretty straightforward. Ugly number is really straightforward, so I guess I wasn't sure what they meant, but they said the prime factors are 2, 3, and 5, so I thought negative numbers would be fine. But they're literally saying if the number is negative, it's actually impossible. So if the number is negative, return false. And then while the number is 1, just try to divide it by every single one of these. If you can't, return false, because that we're at a no solution. Like let's say we're at number 7, we can't divide by anything, we return false. Then we just check at the end, is our number 0 or not. Technically, we don't even have to do that. We can just do this. and then we can return true here because we will never be at 0. I think that'll work too. Yeah. So this would work as well. Palindrome number, easiest way, just turn your number into, so first of all, if it's negative, you can see a negative can never be a palindrome because you have this negative sign, so like negative 121, they're including this as like a letter, so you can't, any negative number won't be true, but you're basically taking some number, turn it into a string, and you can have a left and a right pointer like normal in a palindrome, but you could just do this, and this will do it for you, right? So you literally just say like, take my string, compare it to the reverse. If it's equal, it's a palindrome. So that's a one-liner for that. But obviously, if you got interviewed on like how to do it, I probably wouldn't have this kind of solution, I think. Also, the problem with this solution is you are actually using more space because this x minus 1, you are creating an extra string, but without this, you just have a left and a right pointer, and you just loop through that. I mean, I have like 10 palindrome problems that I've done already. Okay, so let's do the time and space complexity for these. And we're going to be done. Yeah, so let's just say time. And for these, I'm going to say that I'm not going to say these are extra space because I'm using the variables I had. So we do have this res, and if we're not counting res as part, or sorry, actually that would be space. So time, we are just looping through the entire string, so it'd be max length of whatever's longer. So max length of A or B, right? We have to loop through the entire string, whichever one's longer, and then that's going to be that. For space, it's going to be if you're not counting the result, it's O of 1. Otherwise, space is going to be the same thing, max length of A or B. Usually you don't count the result, so I think it should be O of 1. Missing number is time is going to be O of n. We have to loop through the list, and then space, we don't make anything extra, so O of 1 there. Reverse bits, so space or time is going to be log n. Is it n log n or? Yeah, so I think it's log n here, I believe. Yeah, it's log n because we are dividing the number by 2 every time. So time is log n, space is, once again, if you don't count the res as part of it, it's going to be O of 1. Okay, counting bits. So yeah, our solution is actually n log n here, and I might make another video on counting bits in the more clever solution in the future, just because I don't want this video to take up too much time. Okay, so time is going to be n log n, because for every single number, it's going to be log n to get the bits. Because if you think about it, if you have some number, like, I'll just show that real quick. See, we have like 1, 0, 1, 1, whatever. Every time we shift, we're dividing by 2. And so we have to do this 2 to the n times to get some number. And so that would be log n of how many times we'd have to. So sorry, we divide, this is 2 to the n equals the number, and then we're moving it n times. So that would be log n. Okay, and then space. If we don't count the res again, right, we're not making anything else, I believe. Yeah, we just have some temporary variables there. Number of 1 bits for a number is just same thing, I think. So it's going to be O of log n space O of 1. We are not doing anything special. Single number. So here time is going to be O of n because we're looping through the whole array. Space is going to be O of 1, not doing anything special. So Roman integer, so if you were to implement this in the hash map, let's think about that, and space, like what I suggested. I mean, honestly, with this if thing, it would still be like you have a constant number of else ifs, so like say you have 10 or whatever, so that rounds to 0. So you have to go through the string and you just have to check what it is. So I think that's going to be O of n. And then these, like if you had a hash map with, you'd have constant lookups. So space, if you did have a hash map, it would be O of 1 because you'd only have a hash map of like 10 items, which would round to a 0 because it would be a constant number. Okay, shift grid. time is O of n, or sorry, it wouldn't be O of n, it would be O of m by n. We're going through the whole grid twice, and we did make an array that's size O of mn. And so I think there are other ways to do this. There might be a way to do it actually in place. There probably is a way to do it in place, but this is cleaner. And the other way, where if you just move every item once or something, that's going to be way longer because you're doing it mn every time. So that's going to be more like kmn for time because you're moving it only one at a time, right? Like, so let's say you didn't make a new array, you just move everything once, and you do that k times. That should be longer if k is a big number, which, I mean, yeah, it's only 100, but I mean, yeah, these are even smaller, so it's still more efficient. Okay, I guess for the easy problems, they usually give you small constraints because they want just anything reasonable to pass. They're not super concerned with like the best possible algorithm. Okay, ugly number, pretty straightforward. So, oh, by the way, did we go? Yes, we did. Okay, so here it's going to be, so we are dividing by 2, 3, and 5 every time. And so this is kind of similar as divide by 2, except I think it would be still log n, because, so normal log n is log base 2, but now we're also dividing by 3 and 5. But either way, so it might be a little faster than log n, you know, like it might be like log 3n or log 5, depending on what digits it has, but it's going to be like this, I think. And then space is O of 1. Okay. Pounder number. So let's say we didn't create this extra string, right? Because we definitely don't need to. So we turn it into a string, which you can argue is, you know, you can argue is extra space, maybe, maybe not. But either way, there is also a way to do this technically. Yeah, so there's technically a way to do this by doing left to right. And the way, so I guess I can talk about the real fast. So if the negative number was negative, it would still be negative, but what you would have to do is you'd have to have this number, right? And you'd have to create, I think there is literally a problem that's like reverse digits or something. And so that's this problem, you reverse digits, but that wouldn't be an easy problem, right? And the way to reverse digits is you just store this number somewhere and you say like, well, this number is non-zero. We mod the number by 10, so we get this last digit. Then we have some res. And we say like res plus equals or something. Yeah, so we say res plus equals this digit. Then we shift the res to the left, or we multiply it by 10, whatever it is. So let's say 1, this is 10. Now we divide our number by 10. So now this 121 becomes 12, and our res is 10. Then we do the same thing, mod 2, add. So now this is 12. This is 1, and this 12 gets multiplied by 10 again. Then we put the 1 over here, so it would be 121. Then you just check for equality, right? You have two numbers, you just see if they're equal. So that would be the way to do it. I guess we can just say what would be the time and space complexity for that solution. And so for that solution, it would be you're doing every single digit, which would be a log base 10, I believe, because you're dividing by 10 every time. So it's how many times can you divide by 10? So let's just call that log n. And then space for that solution would be O of 1 if you just literally reverse the number. And yeah, because if you have a number, you're doing digit by digit. And then for the string, it would be O of n, and space would be, if you do count the string, would be O of n as well. So I think the digits one is more efficient. It's just a little bit harder to code up, but it's not too bad. It's still like probably like a medium problem or something. Okay, so that's it for this problem. And like I said, I'm gonna probably do one of these, yeah, probably this counting bits one in the future. I'm gonna make a video on that. And so that's the end of the easy speedrun. I hope you enjoyed it. And if you have any other playlists you'd like me to do, just let me know. And like and subscribe if you like this video, and thanks for watching.